Hello, everyone. I'd like to welcome you to our seminar on the use of radar for agricultural applications, specifically as it relates to soils and crops. My name is Dr. Heather McNairn, and I am a research scientist with Agriculture and Agri-Food Canada. I'll be presenting some background slides on radar and specifically trying to relate radar to agricultural targets. And I have with me my colleague, Dr. Jinfeng Zhao, and she will be providing you with a walkthrough of using the SNAP software to process radar data. So with that, we're going to get started on some of the background material. So the learning objectives for this webinar are the following here. We're hoping that by the end of this presentation and demo, that you'll be able to understand how radar configurations affect the responses from soils and crops, what the information content that radar images hold specifically as they relate to agricultural targets, what are some of the optimal sensor parameters that we can use to derive information about agriculture, and then again, my colleague here will be walking you through how to ingest some radar data, how to do some pre-processing, and then how to extract some information on crops and soils from radar data. So for those of us who maybe have come from the optical realm of remote sensing, we know that radar is quite different than optical sensors. So radar is actually an acronym. It stands for radio detection and ranging. And radars operate at much longer wavelengths than optical sensors do. And because of that, they have some special characteristics. So these are all-weather sensors because of the length of the wavelengths. These sensors, this energy is not affected by the presence of clouds or haze or other adverse atmospheric conditions. So this can obviously be a big advantage in areas of the world that are really prone to cloud cover. Because we're operating at much longer wavelengths than visible and infrared wavelengths, these class of sensors also have the ability to penetrate deeper into the target. Sometimes that can be an advantage, and sometimes actually that can be a bit of a disadvantage, but we're going to talk a little bit about that in a minute. Radars are actually also active sensors. That means that they have their own source of energy, so they're not dependent upon just ambient energy. That means that they can operate day or night, and that can be important in regions where we have low illumination, such as polar regions. So let's talk a little bit about the radar geometry so we can understand how we're applying this radar data. So that sort of the natural geometry of a radar is in slant range, and slant range is defined as the distance between the radar antenna. Here we're looking at a aircraft, but this could be a satellite as well. So the slant range is this distance from the radar antenna down to the Earth's surface. Ground range is the distance between the satellite track. So if we take a perpendicular line directly below the antenna, the ground range is that distance between that point and the target. So that's the range direction, is that a cross-track direction. The azimuth direction is a long track direction or the long track distance in a radar image. Incidence angle is also an important parameter that we should understand, and that's the angle between the line of sight of the radar and the vertical to the target. And you see incidence angle here. So it's this angle, and it's a complement of the look angle that we see here. Backscatter decreases with increasing incidence angle. That's an important factor that we should consider, and that rate and function of decrease in backscatter with incidence angle is very much target specific. Next, talking a little bit more about the radar geometry. Radar is defined by two types of two parameters in resolution. That's the range resolution and the azimuth resolution. The pulse length is an important concept to understand as well. That's the duration of the transmitted pulse. And the range resolution depends on the length of that pulse. So shorter pulses, for example, result in higher spatial resolution. But if we shorten the pulse, that means that the transmitted amplitude has to be increased in order to maintain the same total power in the pulse. Azimuth direction is defined by the antenna beam width. That's A in this diagram that you see here, as well as the distance to the target. The beam width is directly dependent upon the wavelength and is inversely dependent upon the size of the antenna. And it's difficult to achieve fine resolutions as that requires very large antennas, which can be difficult to deploy and operate, especially when we're talking about satellites. So let's talk about some of the other characteristics of radar. So I want to talk first of all about radar wavelength or frequency. So in radar, we talk about these two concepts pretty interchangeably. So you're going to hear reference to wavelength or frequency. So radars operate at much longer frequencies than optical wavelengths, so the visible infrared wavelengths that are used in optical remote sensing. Radars operate at about 0.5 centimeter up to 100 centimeters in contrast to those visible infrared wavelengths. And you can see in this diagram here where I've outlined some common frequencies or wavelengths that are used in radar remote sensing, from K-band, much shorter wavelengths, up to the much longer P-band wavelengths that approach about 1 meter in wavelength. So wavelength and frequency are inversely related through the speed of time, and there are some concepts around the waveform that we should be aware of. So wavelength is this distance between 2 points in this waveform, and you see it described here. So that's what we're talking about when we're talking about K-band or C-band or L-band wavelengths. Amplitude is the height of the waveform, and you see that defined here. And we have this concept of phase as well. So phase is the position of any point in time on the waveform. And you see if we have two waveforms, for example, they can be out of phase. And this phase difference is shown in this particular diagram. So the next concept to talk about is the radar polarization. So polarization is defined as the orientation of the electric field of the electromagnetic wave. And to grade a wave, what we need to do is we need to simultaneously feed the radar antenna with components in two orthogonal polarizations, or two polarizations that are at right angles to each other. The electric field is equal to the vector sum of the horizontal and the vertical polarized waves. And it's the phase difference between these two components that we feed through the antenna that determines whether a wave is linearly polarized, which is what we typically are working with in many of our radar applications, or whether if there's a phase difference between those two components, the wave can be elliptically or circularly polarized. So here's an example of a linearly polarized wave. This is what you will commonly encounter when you're using most of the current satellite radar systems. So linearly polarized waves, there's no offset between that transmitted horizontal or vertical wave, and that means that the wave is propagated in a plane. So SARs typically transmit in one or more polarizations and then receive or record the amount of energy scattered back in one or more polarizations. So some of the typical radars that we're working with may be recording information in like polarizations. So that means that the wave is transmitted, for example, in a horizontal plane and received in a horizontal plane, or the wave could be transmitted in a vertical plane and received in a vertical plane. Or we can have radar sensors recording at cross polarizations. In this particular case, it means that the radar is transmitting in a horizontal polarization, but receiving in the polarization that's orthogonal to that transmit polarization. So we can have a horizontal transmit, vertical receive, or transmitting vertically and receiving horizontally. And we consider HV and VH, those two cross polarizations, to be identical, and reciprocity between those two are assumed. We do have other classes of polarizations, one in particular called compact polarization. In this particular case, we are transmitting right circular polarization, and we're receiving horizontal and vertical polarizations coherently. And what's important to understand from a target perspective is that these polarizations affect the interaction with the target, and we'll see that in some of the examples later on. There's also this concept of fully polymetric SAR, so I wanted to take a minute to explain a little bit about what fully polymetric radars are. So these particular radars transmit and receive two orthogonal polarizations, typically horizontal and vertical, but they also retain the phase between these two polarizations, and we talked about that concept of phase a few slides ago. Because we have two orthogonal polarizations and we have phase as well that's retained between those two polarizations, that allows us to characterize completely the scattering field of our target. And this is important for many of different reasons. With these coherent systems, these polymetric radars, we can do a lot of different information extraction from a single radar image. So we can take a fully polymetric image and we can synthesize any polarization. So we talked about linear polarizations being what we commonly see on some of our satellite SAR systems, but we can also synthesize circular polarized waves or even elliptically polarized waves if there's an advantage from a target perspective to do so. We can also determine what the degree of polarization is, and that really more relates to how random the scattering is within a target. And we can even decompose the radar signal to determine what type of scattering is occurring. And here you see some examples of different types of typical scattering that we would decompose for. So we can understand from any particular resolution cell how much of that cell is coming from direct surface scattering, how much of the signal is occurring because there's two bounces occurring when the radar is interacting with the target, or even how much of the scattering is coming from multiple scattering, so more than two bounces. So these fully polymetric radars provide a lot of additional information above what we might get from, for example, a single linear polarization image. So now I want to move on and talk a little bit about how radar is interacting with the target and specifically with agricultural targets. So radars basically respond to two fundamental characteristics of an agricultural target, both the structure and the moisture in the target. So first we're going to talk about structure, and for soils we're really thinking here about how rough the soil surface is. So roughness is defined in radar terms and with respect to the statistical variation of the random component of the surface height relative to a reference surface. And you can see that particular concept demonstrated here. So the random roughness is that variation about a surface that is fit through that rough surface. And we refer to that as the root mean square RMS height. When we think about agricultural targets, when a producer, for example, tills his field, he will probably create some sort of roughness due to the tillage implement that is applied. But in agriculture, we can also think about, in addition to the random surface roughness, we can think about periodic surface roughness. And you can see an example in this picture here. This is a seed bed that's been created. And so we have a very smooth surface in terms of random roughness, but we have these very significant periodic structures in the field as well. So roughness can relate not only to the random surface roughness, but to these periodic roughnesses as well. So again, in terms of agriculture, roughness is primarily determined by agricultural practices, tilling, seeding the field, for example, and they can also relate to modifying factors such as erosion that might occur due to wind or water or other weathering effects. So how does roughness affect radar backscatter? Backscatter increases as surface roughness increases, and so the bottom line here is that rougher soils appear brighter in radar images. And I've just shown three examples here. We have an agricultural field here where this particular field has been harvested, but it has not been tilled, so the producer hasn't tilled this field, and you see that the surface is pretty smooth. We would expect a very low radar response from this type of target. On the bottom left side here, we see a different agricultural field, so there has been some tilling applied to this field, so it's not completely smooth, and we have some random surface roughness, and we would expect sort of an intermediate amount of scattering from that surface. And on the bottom right side, this is a field that has been moldboard plowed, and we see very large structures, random structures that have occurred because of this tillage, and we would expect a much higher scattering from a target like this. But what we need to remember is that the impact of roughness on backscatter very much depends on the frequency and the incidence angle. And this is related, the effect of roughness on radar scattering is related through this criterion, which we call the Rayleigh criterion, which defines roughness as a function of both the wavelength and the incidence angle. So I want to show you some concrete examples of what I mean by this relative sense of roughness to radar backscatter. So what I've done here is I've calculated this H factor relative to different incidence angles. So we have incidence angles at 30 degrees and an incidence angle at 50 degrees. And I've looked at some common radar satellites here, TerraSAR X, RadarSat-2, and Pulsar, ALOS Pulsar. So this is X, C, and L band. So they have different wavelengths, and we have different incidence angles. So in this particular case, roughnesses that are less than have less than this RMS height would look smooth to these particular sensors. So you see, for example, in TerraSAR X, it doesn't take a great deal of roughness for that sensor to see that surface as being quite smooth. So you can see in this particular example how incidence angle and frequency make this impact of roughness on radar return to be quite relative. And in this particular table on the right here, we have different tillage implements and typical random roughness that we expect from these types of implements. So we have moldboard plows that create a lot of roughness, and then we have fields that haven't been tilled and have very little roughness. And what I've outlined in here is what these would look like from these three different sensors, from the X, C, and L band sensors. So you can see from TerraSAR X, for example, that sensor, because of the very small wavelength of X band, that it would see most of these different tillage fields as being rough. Whereas as RadarSat-2, some of these fields would look rough to RadarSat-2 and some fields would look smooth. And these longer L-band wavelengths, most of these fields would look smooth to this particular sensor. There is a complicating factor in radar when we think about tillage or even row directions as it relates to crops, and that is this effective look direction. So the look direction of the radar relative to the row direction can significantly impact the radar return. And this creates these so-called bow tie effects, and we can see them in this example of some airborne data. So this is a particular field, and we have variations in backscatter within this field, and that's because there is a row direction in this field, and the radar, the relationship between the radar look direction and this row direction can set up some very different scattering effects. So the strongest backscatter results are seen when the radar look direction is perpendicular to the direction of the row. And these row effects could be a result of planting, it could be a result of tillage, or even harvesting. What's interesting to note is that we see these impacts of look direction on row direction in the like polarization. So in this case, we're looking at C-band at an HH polarization and C-band at VV, and we see these bow tie effects, these very significant difference in backscatter within any given field. Whereas in the cross polarization, we don't see that type of bow tie effect. So that's one advantage that the cross polarization has in agriculture, and particularly when we're looking at tillage, is that the cross polarization is unaffected by these look direction effects. I want to talk now a little bit about the second part of what's important in terms of radar response, especially as it relates to soil and crops, and that is how much water is in the particular target. So we know that SAR is sensitive to moisture, but the question is, why is that the case? So a microwave that is propagated from a radar antenna will continue to propagate until it encounters what we call a dielectric discontinuity, and that happens when water is present in the soil. So as soon as the radar wave encounters water in the soil, then there will be a response. The dielectric constant is actually a measure of the ease with which dipole molecules, and water is a dipole molecule, so it's the ease with which that molecule is rotated in response to that applied field. So you see this this little cartoon that is displaying here, and we have the wave that's propagating. It is rotating that molecule, in this case a water molecule. The energy of that wave is held in that molecule, and then once the wave passes, the energy is released. So when an electric field is applied, that free water molecule easily rotates, and then when the wave passes, the energy that's stored in that rotation is released. So the real dielectric constant ranges between 3 in very dry soils up to a dielectric constant of 80 if we have significant water in the target. So what does this mean for radars? Well, there's a strong positive relationship between the real dielectric constant and SAR backscatter, and a strong positive relationship between the real dielectric constant and soil moisture. And so what that means, in essence, is that when we have greater water in the target, we have higher backscatter or brighter returns. And this applies, I've been talking about soil, so how much water is in the soil, but it also relates to vegetation. So the more water in a vegetation, the higher the radar response will be. We have to be aware of this concept called penetration depth, and that is defined in terms of how deep the radar wave penetrates into the soil and into the crops. And it's defined by this equation. So the penetration depth, or the depth at which a radar wave will penetrate into soils or crops, is directly related to both the dielectric and the wavelength, as well as the incidence angle. So penetration depth increases as the wavelength increases, and it's greater when the target, whether we're talking about soils or crops, is drier. I want to move on now and talk about vegetation. So we've talked a little bit about surface roughness in radar, and we've talked about the soil dielectric as it relates to water in soils. Now let's talk about vegetation. And we have to remember that the scale at which radar microwaves interact with crops is very different than the scale at which optical wavelengths, infrared, and visible wavelengths interact. So here, scattering with these longer wavelengths is driven by different scale of features. So the amount of scattering is really dependent upon the structure of the crop. So this could be the size of the crop, the shape and orientation of leaves, or the stems or the fruit of the crop. And it's also, as we were just talking about, related to the amount of water in the vegetation as well, but this is at the molecular level. And I've just shown here some 3 common crops. This is a little cartoon of a soybean crop. Here we have the structure of a wheat plant, and here's the structure of a corn plant. And so the amount of radar, both the intensity and the characteristics of the scattering from these crops, is very much dependent, is very different among these 3 crops, because the structure of these crops is different. So you can see that the orientation at which these stems interact are connected with the stem, the main stalk, and the shape and orientation of these leaves are quite different. And that's why we see differences in radar responses among different crop types, and even as the crop structure changes as the crop goes through its different phenological stages. So scattering from crops can be quite complicated. There are many different types and combinations of scattering that can occur, and here you can see in this cartoon some of these different interactions. So we can have direct scattering from the crop canopy itself, particularly if the leaves are quite large relative to the radar wavelength. We can have direct scattering directly from the soil, or we can have any number of multiple scattering events that happen within the crop canopy itself. So these scattering events determine how much of the energy gets returned back to the SAR sensor. And it also determines, for example, how the phase between the horizontal and vertical components change. So that can create differences not only in the intensity of the radar that's scattered back, but also the phase characteristics of the radar. And the good thing is, because that changes with different crop types and different crop growth stages, that allows us to derive important information about the crop canopies. As I was talking just a minute ago about the importance of thinking about the wavelength scale relative to roughness on soils, that's true also of crops. So we also here have to think about the frequency as it relates to the structure of the crop components. So canopies can attenuate radar microwaves, or they can scatter radar microwaves, and it's dependent on many different things, but it is very much dependent upon the size of the scattering components in the canopy relative to the wavelength. So if we have large canopy components, this is a corn leaf, for example, we will have more direct scattering from that corn leaf, particularly if the radar wavelength is quite small. In other cases, such as wheat, for example, we can see attenuation of microwaves, especially if we're looking at shorter wavelengths. The frequency also affects the penetration depth into the canopy. So with longer wavelengths, such as L-band wavelengths, we'll see a greater penetration into the canopy. And that means that there is more multiple scattering that can happen within the canopy and greater multiple scattering between the canopy and the soil surface as well. In terms of soil moisture, longer wavelengths like L-band, they tend to be better for soil moisture retrieval because there's greater penetration through the canopy and greater interaction with the soil surface. When we think about crop classification or modeling biophysical parameters of crops, the exact radar frequency that's best is not an easy answer. It really depends on the canopy components itself, because remember, all of this is relative to the wavelength and the scattering components. So we need enough penetration into the canopy to interact with the canopy, so the stalk and the fruit and the leaves of the canopy. So L and C band for corn, for example, tends to be a good frequency, but we don't want too much penetration into the crop canopy so that we have significant interference from the soil. So we tend to think about, again, these longer wavelengths to be better for large biomass crops, but lower frequency or smaller wavelengths, C and X band, for example, tend to be better in terms of deriving biophysical information about lower biomass crops like soybeans. So there's no simple answer in terms of what the best frequency is for deriving crop information. In terms of polarization, polarization affects how the microwaves interact with the crop canopy. Vertically polarized waves tend to couple more with vertical polarized vegetation, and more energy tends to be attenuated at vertical polarizations. Horizontal polarizations in general, we see a greater penetration through the crop canopy and interaction with the soil surface. But by and large, the best single polarization, whether we're talking about identifying different crop types, so for crop classification or for deriving biophysical parameters, is the cross polarization. So that tends to be the single best polarization, and that's because that cross polarization is really reacting or interacting with the is primarily creating multiple scattering events within the crop canopy, and that tends to be very much related to the type and condition of the crop. The next best polarization tends to be that vertical polarization. When we're looking at the third factor, which is incidence angle, it tends to be less of a critical parameter in terms of what is the best incidence angle. It tends to be less critical for crop classification. Here at Agriculture Canada, we use a variety of different incidence angles in our crop classification. If we're looking at temporal changes, so if we're looking at changes in biomass, for example, over time, we don't want to mix our incidence angles because, as we learned previously, incidence angle has a significant effect on radar return. For biophysical estimation, if we have a model that parameterizes incidence angle, such as the water cloud model as an example, then we often do use different incidence angles in our biophysical retrievals. So let's talk a little bit about some of the complications related to the environment. Radar is considered an all-weather sensor, and that means that we can acquire imagery regardless of cloud cover. But we never want to use radar if it's raining at the time of the acquisition. And that's because although radar is considered an all-weather sensor, it does not include imaging during rain events because water in the atmosphere can cause scattering of the radar signal. So one thing to be aware of, in some regions of the world, the risk of rainfall is diurnally dependent, and so we may want to consider acquisitions during morning or evening depending on what those risk factors are. The second environmental condition we should be aware of is that these freeze-thaw events. So we never want to use radar if the ground is frozen, and that's because the dielectric constant falls to close to zero when water changes to a frozen state. And that means that even though there could be water in the soil, the SAR would view that soil as being quite dry because the dielectric is so low. So SAR can detect freezing and thawing. That's a good event, or that's a good thing if we're looking at freeze-thaw events. But if we're looking at detecting soil moisture in, for example, we want to make sure that we're not acquiring radar data during times of freezing. So in parts of the world, for example, freezing often occurs in the overnight hours. So we want to avoid most likely collecting radar in those early morning time periods. Dew on either soil or canopy during early morning hour acquisitions is also something that we want to be aware of. So the presence of water on leaves that accumulate overnight due to high humidity and falling temperatures can leave water on the leaves, and that can increase the radar backscatter. So if there's water on the canopy is significant after rainfall or due to this overnight formation of dew, then that can create significant scattering of the radar signal. So whether we're talking about rain events that can happen diurnally, whether we're talking about freezing or thawing of the soil surface, or we're talking about the formation of dew on the canopy, these are environmental factors that we should be considering. We should always be checking the meteorological conditions so that we know whether it was raining during the time of acquisition or whether the target was frozen at the time. And as I've listed here, sometimes we can select particular orbits. So ascending evening orbits can be selected, for example, to avoid overnight freezing or formation of dew overnight. Or we might consider selecting morning acquisitions if, for example, the risk of rainfall is less in the morning. So always check the meteorological conditions and think about which orbit is best suited to avoid these environmental conditions. And finally, before we hand it over to Nina to go through the SNAP demonstration, I want to talk a little bit about noise in radar. So when we think about radar, each resolution cell of a radar image is composed of many different scattering elements that contribute to the radar scattering. And these scattering waves have phase that are determined by these scattering elements. So in any particular resolution cell in a radar image, the response in that resolution cell is a sum of not only the intensity or the amplitude of the scattering that occurs, but it's also the phase that is occurring among these various scattering elements. And you see an example in this diagram here. And all of these scattering waves can lead to interference. So we can have constructive interference where the phases add up to create higher radar response than we would typically expect from that target. Or we can have destructive interference where these waves, because of the different amplitudes, because of the different phases, cancel each other out. And that's why we get this salt and pepper noise effect in radar imagery. There are ways that, various processing ways to reduce the effects of speckle before we do any information extraction from radar. Multi-look processing is one typical way to reduce speckle noise. And this is where we divide the radar beam into several narrow sub-beams, and each sub-beam provides an independent look. And then we sum these looks up to form a final output image with reduced speckle. Typically, users, however, are going to apply either a spatial or a temporal averaging speckle during their image processing. And so there were special speckle filters that have been adapted for radars that we apply to the radar to suppress that speckle noise. So at this point, I'm going to hand it over to Nina, and she's going to take over on the SNAP demonstration.
Hello, everyone. Today, I will use RadarSat-2 SLC data and Sentinel-1 as an example to show you how to ingest, pre-process, and process SAR data for use in crop classification and soil moisture estimation. I will prefer this SAR processing with SNAP toolbox. SNAP is open source software for Earth observation data processing and analysis. Today, I will have two major areas we'll cover. The first one is extract backscatter and polymetric parameters from RadarSat-2 fun quad-pol SLC data. The second main part is processing Sentinel-1 data for crop classification. So I will show you how to use RadarSat-2 data to extract backscatter. So there's 4 main steps to extract backscatter. First, you need to read the data into SNAP and calibrate the image, convert image value to radar backscatter. The second step, as Heather talked about, need to apply sparkle filter to remove SAR sparkle from the image. And the last part is apply terrain correction to perform also rectification. And I will walk through all these steps with a SNAP. The first step we need to inject SAR raw image. We'll do So I have one RadarSat-2 fun quad-pol SLC data. SNAP is able to inject raw RadarSat image in zip file. So I select that zip file is open. So you have this image load into the SNAP. That's the raw RadarSat image. So the second step, we need to calibrate the SAR data, convert pixel value to SAR backscatter. We need to click radar, radiometric, and then calibration. You will see this window and select the source, your raw RadarSat-2 image. Type in the output, the file name, and select the folder where you want to save the output image. From this process parameter type, to extract radar backscatter, we just leave the default here, and then we hit run. So right now we have the calibrated image load into Explore window. like this here. So we see the radar set 2 for polarimetric backscatter here. The next step is applying the sparkle filter. So you click radar sparkle filter. We only have one acquisition, so we select a single product sparkle filter. So here you see there's a window. Once again, you select the source image, that's your calibrate radar set 2 image, and give the output name and select output folder. For process parameters, with the snap, there are several sparkle filter we can select. Today we look at gamma map filter. So we select gamma map filter and give the filter windows. Here we just give the 3 by 3 windows to filter the entire image. So we hit run. Okay. So we have a filtered image upload to Windows Explorer. Just filter the HH backscatter image. So for this processing, the next step, we apply terrain correction to also rectify the image. We click radar geometry, terrain correction, range duplicate terrain correction button here. Once again, select the filtered SAR image and give the output file information here. There are several parameters need to select for the terrain correction. So click Processing Parameter tab here. So for DEM model, we usually select SRTM 3-second model. The software will automatically download that DEM. And for resampling method, we select bilinear interpolation here. For radar set 2 data, we give 10 meters special pixel spacing here. For map projection, we keep WGS84 projection here. So after we give all these processing parameters, we can hit run here. Okay. So the process is finished. So we have also rectified SAR image load up here. So that's after that 4 steps, calibration, SAR sparkle filter, and terrain correction, we have 4 polymetric backscatters extract from radar set 2 SLC data. So we can load the RGB image here, HH, HV, and VV. So that's the RGB image. That's from radar set 2 data. Moving on. I will show you how to extract the polymetric parameters from radar set 2 front quadpole SLC data. The same as extract backscatter from radar set 2 data, you need read the data into the snap, calibration the data to SAR backscatter, apply sparkle filter, and then perform polymetric decomposition. The last step, the same as a backscatter extraction, is a terrain correction to also rectify the image. So I will walk through all these steps with a snap. The first, we load the radar set 2 raw image here. From that band quadrupole SLC data, we see the full polymetric information here. So they have an intensity, backscatter intensity, and also they have a phase information here. There's a complex data contain the phase information here. So the next step is collaboration. So the same as radar backscatter extraction, we collaborate the raw image to radar backscatter. Here, we select the raw image, give the output information, and that's for polymetric parameter extraction. It's important to hit the button here, save as a complex output, because for polymetric decomposition, they need complex data to generate a covariance matrix. So we run this collaboration. After collaboration, we change the image pixel to radar backscatter. And the next step, we need to apply polymetric filter to remove the radar speckle. So we hit radar speckle filter, single product filter, speckle filter, select calibrated image. And for processing parameters, we select boxcar filter. So boxcar filter is a polymetric filter. They keep the phase information after the filter. We hit run. Okay. So after we apply the boxcar filter, we have a filtered image with intensity backscatter here. After that, we need to apply polymetric decomposition from radar to polymetric decomposition. From here, we select filter the image, and then give the select decomposition method. So today we look at the proven Dielectric decomposition. We give the decomposition window as 5 pixels. So we hit run. After apply proven Dielectric decomposition, we have 4 polymetric parameters: double band scattering, volume scattering, and surface scattering. The same as extract radar backscatter from radar set 2 data. The last step is apply terrain correction to the image to also rectify the SAR backscatter. So radar geometry, terrain correction, range Doppler. So select decomposition parameters here and give the output image file and output folder you want to save the image. For process parameters, you select the DEM model and resampling method. So the same as a backscatter extraction, we select SRTM 3 seconds DEM model and bilinear interpolation method. For radar set 2 data, we give 10 meter pixel spacing, and for map projection, we use WGS 84 degree projection. So you hit run. Now we have also rectified polymetric decomposition parameters. Upload to Explore window. We can load RGB image here. That's polymetric parameters from Furman-Dilton decomposition. So far, I have shown you how to extract backscatter and polymetric parameters from radar set 2 data. So use extract backscatter, we can calculate soil moisture from radar set 2 data. So we can produce soil moisture map from radar set 2 data. To extract soil moisture from radar set 2 data with SNAP, you need install soil moisture toolbox first and make sure you have a land cover map installed in your local computer. So for soil moisture toolbox, there are several methods can extract soil moisture information from radar set 2 data. Today, I will show you how to use a multi-angle pre-processing and IEM model to extract soil moisture information. There's a snap graph show you step by step how to process radar set 2 data and export soil moisture map. To perform multi-angle inversion method, you need 2 radar set 2 acquisitions, one in the morning and another one in the afternoon, 1 day apart. So with the snap, close all the products here, and with the snap, you can load in 2 raw radar set 2 image. One in the morning, another one in the evening. So, and use that snap graph, specify 1 raw image in the morning, and the second input, the image in the afternoon. So if you hit run, this graph will process the image automatically, and you will have a soil moisture map after the program finished. That will take a little bit time. I have an image. That's the output image from that graph. That's a soil moisture map. That's a soil moisture map extract from the two radar set to raw image. Because of this inversion model, the soil moisture map only produced from the overlapped area of that two image. So far I have finished the first main part, show how to process the radar cell 2 image with a snap, and moving on. And now I will moving on to how to process Sentinel-1 data for crop classification. I will close all this stuff. There are several websites you can download Sentinel-1 SAR data. So I download the Sentinel-1 data from Vortex. There's a ASF portal. So I download 3 acquisitions in 2012. And for process Sentinel-1 data, that's steps for process Sentinel-1 data, the same as process radar set 2 data. You need to inject the image to snap and apply orbit correction, apply multi-look, calibrate the image to SAR backscatter, apply sparkle filter, and carrier correction to also rectify the image. I will walk through that step with a snap. Now, for the snap, we need log in. Need read one image. So Snap is able to read a zip file. So click. That is a Sentinel-1 IW mode. RGDH level 1 data has a 20 by 22 meters resolution, and it is a multi-look image, has 5 by 5 looks. The next step, we need to apply orbit correction. So we select the raw Sentinel-1 data here and give the output information, output file information here. And for process parameters, we select process orbit information. The program will automatically download the process orbit information to apply the image. So we hit run here. Process finished. Sentinel-1 GRDH product, it is a multi-looking image. If you want to further average the power in both azimuth and range direction, you can apply the multi-looking process here. But this multi-looking process for RGDH product is optional. So if you want to perform multi-looking, so go to radar multi-looking and select orbit correct image from the process parameter type give number of range loops and the number of Edman loops. For this application, I gave 3 range loop and 3 Edman loop. So we hit run. So now we have a multi-loop Sentinel-1 image here. The HV backscatter, that's the HV backscatter. So the next step, we need to calibrate the image, convert the pixel value to SAR backscatter. So the same as the radar set 2 calibration, we go to radar radiometric calibration. So select multi-loop image and give the output file name and the folder you want to save the data. So from this tab, we do not need change any parameters. So we have a VH and VV polymetric backscatter and the output as a sigma 0 band. So we hit output. We have a calibrated Sentinel-1 data here. So for any SAR image process, sparkle filter is a very important step. So the next, we apply sparkle filter for that Sentinel-1 image. So we can hit radar sparkle filter, single product sparkle filter. We select calibrated image, and for process parameters, we select the several filters we can select. So right now we select gamma map and give the filter window. So we choose 3x3 filter window. So we'll hit run. Okay. So the filtered image pop up for this explore window. So we have filtered VH, VV backscatter. So the last step, we need to also rectify the filtered image. So we go to radar geometric terrain correction and do range duplicate terrain correction. We select filtered image and select the DM model and resampling method. For this Sentinel-1 image, we gave 20 meters pixel spacing and keep the WGS84 map projection. So we'll hit run. Okay, this process will take a little bit time. I have the output here. We'll stop this process. That's also rectified Sentinel-1 data. So we can have RGB data. Look at this. So far we have finished the process Sentinel-1 data. So I have 3 acquisitions to use that 3 acquisitions for crop classification. So I will load all these 3. So here I have make this connect. So here I show you 3 days Sentinel-1 image. This one acquired on June 13th. The second one acquired on July 7th, and another one is July 31st. So I will use all these 3 images to perform crop classification. So to use all these 3 acquisitions for crop classification, we need co-register all these 3 images together. So we can add the image. Use this button, add all these 3 images first. So we don't need this image. There's all 3 processed Sentinel-1 image here. And if you hit the run button, it will give you co-registered image. This process will take a while. I have an output here. So we'll see all 3 days image in one snap file. So today we were looking at supervised crop classification. To have a training data, we have a ground crop survey data serve as a training data, and you need to modify this ground survey data to generate this survey data as a ArcGIS shape file. So once you have ArcGIS shape file, you need to import the shape file to Snap. So you have to open the co-registered image and then go to Vector, Import Shapefile. So we have a canola training data here. So we use the crop. We import another crop vector. Shapefile. You have a soybean import here. Collect crop. I'm trying to look at the polygons here. import another crop. Okay. So after you import the training data, you can perform classification from raster classification. So we look at random forest classifier here. So we add the data. Remove this. So we add the co-registered image here. And for that type, random forest classifier needs to select the numbers of training samples and number of trees. We leave this as a default. So if you hit run, you have a classification map. That will take a while. I have a output here. You double click this label, you will see this classification map here. From this color manipulate tab, you see the crop class here, canola, corn, soybean, and wheat. And you can change the color a little bit here. So I have a file. That's the final classification map. The bright yellow color is the canola, and the orange one is the corn. The green is the wheat. And the soybean is the blue polygons. So that's the final classification product. We use 3 days Sentinel-1 data.
So what we see on the screen here that Nina has produced is a map of crop classification that has been produced with these 3 Sentinel-1 data. And as she was saying, we have 4 different crop types here: canola, corn, soybean, and wheat. We map crop type in Canada every year, so this is sort of a base information that we use for a lot of different purposes. For example, this type of crop classification methodology can identify acreages of crops grown. That's a very important sort of statistical parameter that we need to understand in terms of who's growing what where and how many acres of different crops are being grown. It's also a very fundamental layer for a variety of other things. So, for example, we're often quite interested to know what the productivity of crops are. So that could be looking at just the changing productivity of the crop over the growing season, or we may be using crop process or crop yield models to do that. Those models tend to be crop type specific, so understanding what the crop type is sort of a fundamental information layer that's used to provide information in terms of not only what acreages are growing, but what the productivity, so yields per acre that of different crops that are being grown. We also want to understand, for example, risks due to different crop diseases, and this type of base information in terms of crop classification is very important information in understanding risk due to crop diseases, for example. So, for example, some diseases perpetuate themselves when we're growing the same crop year after year. So understanding what crops are being grown on what landscapes and how frequently those crops are being grown in any particular field helps us understand different risks due to crop diseases as example. So crop type information is very basic information, whether we're looking at crop statistics in terms of acreages being grown, whether we want to understand what the crop productivity is and using yield models specific to different crop types, or whether we're concerned about risk to crop production, for example, from different crop diseases. So it is really a very basic piece of information that's required in agriculture. Just a little summary of what we've learned today. We talked a little bit about some of the radar parameters. We covered frequency and wavelength, talked about polarization and incidence angle, and specifically how those relate to both soils and crops, and why we can use radar data in different frequencies and polarizations to extract information about things like soil moisture, crop type, and crop condition. And then Jin Fang, or Nina as I refer to her, walked us through a demonstration using Snap. So remember, Snap is open and freely accessible software that you can download and get started right away on processing some radar data. She read in some RadarSat 2 fully polymetric quad pole data and extracted backscatter at different polarizations. She ortho-rectified and filtered that imagery. She then read in some polymetric radar data, again applied some filtering ortho-rectification, and was able to derive some polymetric decomposition, surface volume, and double bounce scattering from the RadarSat 2 data. Nina then walked us through using the soil moisture extension that you can download for Snap, using 2 quad pole RadarSat 2 images to be able to extract surface soil moisture, so volumetric soil moisture from those 2 radar images. And finally, Nina showed us where we could access Sentinel-1 data and download it, how we can read that Sentinel-1 data into Snap, again, transforming the data to backscatter intensity, ortho-rectifying and filtering that data. And then finally, if we can load in 3 Sentinel-1 images together, along with some training data, performing a supervised classification in Snap. So now we'd like to open up the session to question and answers. We'd ask you, if you have any questions, that you type them into the question box on your computer, and we'll be happy to answer any of those questions that you may have.
Thank you very much for that presentation, Dr. Heather McNairn and Dr. Jianfeng Zhao. Now we'll open this to questions, and we have here a list of questions that you've been already typing. So let's just make sure that our invited guests are online and can hear us.
I can hear you. Can you hear me, Erica?
Yes.
Excellent. So do you want me to just read the questions and proceed to go through them, or are you going to read the questions, or how would you like to do this?
Yes, go ahead. You can go ahead and read the questions, and we'll go one by one.
Can you make your screen a little bit bigger? Okay, yeah, I think that's fine. So question number one is how to extract SOAN area from Sentinel-1 data. Which polarizations, VV or VH or both, should be used? So this is a good question. Let's talk about the polarizations first. So when we think about, this is sort of a general comment, but when we think about crop classification or land cover classification, which this question sort of refers to, generally the cross polarization VH or HV tends to be the best single polarization for land cover classification or for classifying crop types. So that's generally the polarization that we think of first. But VV polarization, tends to add some additional information as well. So I guess yeah, we're just trying to fix our screen here. I guess the answer here is that VH is probably the best single polarization. VV is probably the next best polarization. And generally we use a combination of those two. So in our crop classification operation that we do in Canada, we use both those polarizations, VV and VH. But you also tend to have to need a time series of imagery as well. So a single VV or VH image usually doesn't perform that well. So we acquire a series of dual polarization images over time. So that would be the answer to question number one. Okay, the second question, I think I'll just read it. It says the water content impacts the backscatter, but this is always complicated by the solute in the soil. How does this reflect in soil studies, i.e. the salinity studies? So this is a really tough question because we know that the salts in the soil particularly affect the dielectric loss or the imaginary part of the dielectric. So there is an impact on the imaginary part of the dielectric, but that tends to be pretty small when we think about the sensitivity of radar to the real part of the dielectric. Having said that, it is sort of something that we have ignored in the research. So we haven't looked, in any great depth in terms of how to differentiate sort of soil moisture in areas of high salinity versus areas of low salinity. But we do know that dielectric loss part of the dielectric constant is pretty small. So I guess the answer to this is that this is probably something that would need to be looked at a little bit more carefully from a research perspective because there aren't a lot of studies out there. But again, we do know that the salts in soil affect that at least that small imaginary part of the dielectric. So question number 3, for a place like India, how would you account for the monsoon season when it's constantly raining? Some of the data is daily rainfall and not hourly rainfall. So again, that's kind of a tough question to answer. Certainly, we don't, as you saw in the presentation, we don't want to be using radar data if it's raining at the time of the acquisition. And here in Canada, what we do is we look at the exact time at which the satellite comes over, so the exact minute and second that the satellite is imaging. So we tend to go to ground meteorological stations to look for that or other sources of meteorological data. If you don't have access to that data, sometimes you can see these impacts of rainfall in the radar images themselves. And you can typically see these sort of rain cells, that the response in the target, because these tend to look like very washed out areas of the image where you don't see a great deal of differentiation from one field to another. So sometimes you can see it qualitatively in the image. But really your best source is to try to find some meteorological data that is going to tell you whether or not it's raining at the exact time of that acquisition. Because again, we don't want to be using radar imagery when rain is occurring. And if it is occurring at the time, there's really no way to compensate for that. So what we tend to do is we drop that image from our analysis. Unfortunately, that's an image that, that we can't use. So question number 4, can we calculate the amount of agricultural crops using SAR? How much will be harvested from crop X? Okay, so I think this question is maybe referring to sort of productivity in crops. So the short answer to that is yes. There are some methods that have been developed in the last 5 years where we can derive estimates of above ground biomass using radars. We've been doing work with RadarSat 2 and a little bit with L-band radar as well. The methods that we're using are semi-empirical models, so we parameterize these models, and then we use mostly cross-pol and VV backscatter, so 2 polarizations, and we're able to sort of parameterize and then invert the models to estimate above ground biomass. So there are some publications that we have been that we have in the literature, and there are others that have worked on this as well that we can share with the webinar attendees. So the short answer is yes. There are some methods that have been demonstrated to do that, and the crops that we've been able to estimate fairly accurately what the biomass, the above ground biomass is. We've been looking at wheat, corn, and soybeans. So question number 5 is, can you please explain right circular more in depth? Okay, so as we were trying to say in the webinar, the reason that we're looking at compact pole, which uses circular polarizations, is because it allows us to acquire data over much wider swaths than if we're using quad pole data. So for RadarSat 2, for example, the quad pole data right now, the swath width is limited to 50 kilometers. So for operational monitoring, that's not really a big enough swath to be able to provide the kind of coverage that we need. So what circular polarizations do is that instead of sending alternating pulses, transmitting and receiving alternating pulses, so sending a horizontal and a vertical pulse alternating during the transmission, they're sending those pulses at 90 degrees out of phase, and so there's one polarization that's transmitted. So because the H and the V component are being transmitted at the same time, but 90 degrees out of phase, it causes the rotation of the wave in a circular propagation. So you're sending one wave transmitted in a circular polarization, and in the compact pole mode, we're receiving both the horizontal and the vertical polarization separately, but with the phase retained. And to be quite honest, we don't know a great deal right now about what these circular polarizations are telling us about the soils or the crops. We have looked at statistically the correlations between some of these circular polarizations, the responses that we're receiving from them, and what we receive from some of the linear polarizations, and they are fairly highly correlated. So for example, a right circular polarization has a very high correlation with the linear cross polarization HV. And in fact, we are trying to do some modeling right now using circular polarizations for soil moisture retrieval because they are so highly correlated with some of the linear intensity responses. Okay, so question number 6 is, how practical is it to use dual pole Sentinel-1A data to perform crop classification in a multi-crop scenario? So I'm going to answer this question a little bit generally. I think that Sentinel-1 data has a lot of potential for doing crop classification, especially as Nina was showing you, if you use the IW mode, which provides dual polarizations. So if you're using that VV-VH polarization, then that provides some really good scattering information for crop classification. And there's a lot of work being done in demonstrating that this works fairly well. Having said that, the most important part of any crop classification is to have a good temporal coverage. So I always think of it this way: if you have one Sentinel-1 image, VVVH, and you only have one Sentinel-1 image, the likelihood of successful classification is really diminished with just one image. So by and large, the most important aspect of crop classification is to have a good temporal coverage of SAR images through the growing season. The most important time to have a radar image usually is when the crop is in its reproductive stage or when it's developing its fruit, because that's when the structure is really changing. So that tends to be a really important time to acquire this radar data. So I guess in general, to answer the question, I think that Sentinel-1 has a lot of prospect for doing that. And the success, again, depends on the crop types that you're looking at and how complex your agro-ecosystem is. But in general, there's been pretty good success at using Sentinel-1 data, so I really encourage everybody to give that a try. So the next question is more of a processing question. So I'm going to pass it off to Nina, but I'll just read the question here. So what stage of SLC processing is right to work on subsets? So I'm going to let Nina answer this one.
I think when you process SLC data, that depends on which software you use. This depends on the software. When you subset the image, when you click the smaller area, depends on the software can save the SLC data, can output the SLC data. For POSA Pro, if you use a POSA Pro, so you process the entire image, but you can apply a mask. So that's provide an additional layer. So you mask out somewhere you do not want to process. So I think so. Just subset. SLC data and output SLC data. That's really the answer is really depends on which software you use.
Okay, so we're going to move on to question number 8. This is a question around speckles. So it's asking, I think the question here is that speckle is really a phenomenon from the target. Or from the data itself. And so the question is, why is it considered as noise and needs correction? So that's kind of an interesting question. We always think about speckle as noise, but it is a phenomenon of the target itself. So it is sort of a characteristic of the target. So again, you have these individual scattering elements within any radar pixel. So if you think about a corn canopy, you have a lot of different features within one radar resolution cell. And so the scattering that happens within that corn canopy, we get this constructive and destructive interference. And so that causes either significant increases in the recorded backscatter or artificially low responses. So for an individual resolution cell, that's not so meaningful because we do have this, this constructive and destructive response. So if we look at distributed targets, we need to really average over a number of different resolution cells to provide something meaningful for the target. So it's not that I think that the person who posed this question is correct. It's we think about it as noise, but it is really a phenomenon of the data and of the response from the target. But we do need to suppress it because in an individual radar cell, that constructive or destructive interference is not really reflective of the scattering from that particular target. So it's not a question of it being noise per se, but it's a question that we sort of need to smooth out those interference patterns. Otherwise, it's not really that meaningful. Especially for these distributed targets. The next question as well is a processing question, so I'll read it and I'll pass the microphone to Nina. So the question is, can we select a subset of latitude and longitude when an image is flipped and not yet terrain corrected?
So before you apply terrain correction, if you want to subset the image, that use latitude, longitude, you need to make sure that the UU image have a projection. So you need to know the correct need to know the latitude and longitude correlation.
Okay, you're done. Okay, question number 10. So the question is how to differentiate between crop types having similar signatures in different growing seasons using Sentinel-1 data. So this is a bit of a complicated question. I guess the bottom line is that radar is really no different than processing optical data. So if you have two different crops that have the same signature, then it's going to be pretty difficult to differentiate them. That's why it's really important to have multi-temporal data. And again, as I said earlier, probably the most important dimension in classification using radar or optical data for that matter is to have a good temporal coverage. And typically with most crops, there will be a point in the crop development where those crops look different to the radar or to the optical imagery. So sometimes it's a matter of conducting a little bit of research to determine when those time periods are. And unfortunately, if you can't find those, then it's going to be very difficult to separate them. As I said, we can certainly use different polarizations. We can even use different frequencies to try to sort of enhance those differences in signatures. But it's really, again, the time dimension that's the most important, whether we're classifying radar data or optical data. Okay, when using SLC data, when using SLC data is unavoidable in certain applications, scalloping effects are observed during processing. How does one correct that? So Nina and I were debating this question a little bit, and that's a question we don't have an answer to. My experience in scalloping has been from many years ago when some of the first sensors were launched. So when RadarSat-1 was launched, for example, we saw these artifacts of scalloping in the imagery. But honestly, since since the some of the improvements, I guess, in the calibration and the processing of radar data, I haven't seen those effects, especially over distributed targets, like agricultural targets. So quite honestly, that scalloping effect is not something that I have seen recently in some of the more recent calibrated SAR sensors, and it's not something that that we generally see over agriculture errors, or that I have seen at all. So it's not something that we've seen, and it's not something that I don't really even know how you would correct for that. But maybe that's something that Erica or even us, we could check into a little bit more.
Right. So my experience with scalloping, and I think this question pertains to some of the Sentinel-1 images, and it was asked in one of the previous ones.
Okay.
Hello?
Yeah, sorry, go ahead.
Oh, yeah. Okay, so yeah, there are some issues with some of the Sentinel-1 data, and they have these scalloping effects, and basically the data is not usable. It's just it's a full image. So
okay, that's good to know. That's okay. So that's not something that on the RadarSat data that we've really seen in recent memory. Okay, question number 12. How do you decide on the type of filter and the decomposition? Is it trial and error? So the answer to that is a yes, it is. We have actually done through a project that we're leading here at Agriculture Canada, we've done a little bit of comparison of filter types and filter sizes for crop classification. So we picked 3 different sites, one in Canada, one in Europe, and one in South America, and we took a look at different filter sizes to apply. And these different sites had agricultural fields that varied in size. So we did come up with sort of a consensus of what generally the best filter size was for those, but it was a process of trial and error. We tried it, like I said, a few different filter types and a few different filter sizes. So generally, the filter is driven by the size of the filter is driven by the target, so the size of the field. The type of filter, I think there's a question later on. It's going to ask a little bit about why we're using the map gamma filter. The most important thing is that you're using a radar adaptive filter, and so if you're using any of those radar adaptive filters, it reduces the variance, but it doesn't affect the mean significantly. That's why we want a radar adaptive, but the size of filter needs to be a little bit of trial and error. The decomposition method as well is a little bit of trial and error. So some of the decomposition methods produce somewhat similar results, but there are some new decomposition methods like the Tuzi decomposition, the Yamaguchi decomposition, so it is a little bit of trial and error. Nina showed the Freeman-Durden because it's a pretty common one that's used, but I would encourage you to maybe explore all of those different decompositions. So question number 13, can you explain a bit more regarding how the inversion model produces soil moisture? How are the results calibrated to soil moisture measurements? So the soil moisture is using the integral equation model, and so we're using the HH polarization as well as the VV polarization. And so what we've done for the inversion is we've created forward runs of the IM model for both of those different polarizations with increments of different roughnesses and different dielectric constants. And so we create these lookup tables from these forward runs of the IM model for both HH and VV polarizations. And then when we have a radar image with those polarizations, we apply those lookup tables, and we're trying to find sort of the backscatter from the radar image within the lookup tables that sort of minimizes the difference between the radar imaged and what the IM model is estimating for backscatter. And so it finds that it's a minimal search function, and it finds the soil moisture that fits that criteria, is the minimum difference between measured backscatter by the satellite and the model backscatter from the IM. So it's a lookup table inversion approach. The results are validated continuously on our part using in situ station data. So we have a permanent network of in situ stations in Canada. So every time we produce a RadarSat soil moisture product, we are comparing the estimated soil moisture from the IM inversion on RadarSat data to what's measured from our in situ networks. Question 14, I saw you had a download all Python file in your folder. This person is very observant. Is there an API for downloading images from Sentinel-1 or other sources? So this was Nina's folder, so she's going to answer this for you.
Yeah, so it's easy to make a Python script to download all the Sentinel-1 image you want. You just need to specify row and the path and the date, acquisition days, and then you download all the image you want. The question 14 is, at what instance should we apply orbit file? Is this depends on the sensor? Yeah, so for Sentinel-1, so we apply the orbit correction, because if you use the snap, we see that's application. And for Sentinel-1, there is orbit information with your product you download from the website, but we do not sure that product is updated. So before you use this data, you need to apply the orbit information to make sure you have a processed orbit information with your data. That will affect your terrain correction process.
Okay, so question number 16. If the phenology of different crops sown in a particular area is the same, how to classify those different crops using Sentinel-1 image with significant class separability, for example, corn, maize, and groundnut? This is a kind of a difficult question to answer, but you know, again, think back to what we were saying in the webinar, that what's primarily driving the radar responses are changes in structure to the crops. So the examples that are used here, cotton, maize, and groundnut. Groundnut I'm not so familiar with, but cotton and maize, I mean, the structure of those two crops, even if they're in the same phenology stages, the structure of those two crops are quite different. So that's what you're looking for. You're looking for points in the growing season where crops have different structures. So in this particular case, I'm pretty confident if you looked at the VV-VH dual polarization mode of Sentinel-1, you will probably see differences in the radar response because the structures of these crops are quite different. So question number 17, should one perform incidence angle correction and maintain uniform incidence angle in order to obtain obtain soil moisture using Sentinel-1 data? So the first thing I'm going to say about this is that the method that Nina showed you using the IM retrieval, this is one of the reasons why the IM is a good way to go in terms of soil moisture retrieval, because there is an accounting of the incidence angle within the IM. So because of that, we can use radar data at any incidence angle. We mix and match incidence angles all the time when we're retrieving soil moisture using the IM. You know, having said that, as we know, incidence angle has a fundamental effect on the radar backscatter. So if you're looking at retrieval of soil moisture using, for example, a change detection approach, then you would have to collect the imagery from Sentinel-1 at the exact same incidence angle. Otherwise, what's changing from one image to another could be simply due to the change in incidence angle as opposed to a change in the soil moisture. In terms of applying an incidence angle correction, I'll be honest with you, even within our group here, we have a bit of argument over whether we should do this or not. The difficulty in applying a correction for incidence angle, where we're actually sort of trying to apply a function where we remove the impact of incidence angle, is that function of incidence angle, that change in incidence angle, or the change in backscatter with incidence angle, is dependent on the target. So that function is not going to be the same if you have a rough surface or if you have a smooth surface. So it's really difficult to apply one incidence angle correction where you're not actually introducing error, because you're just estimating what that function would be, but it's not the same for smooth and rough surfaces or for different vegetation types as well. So the bottom line here is it's best to use a model that integrates incidence angle as a parameter in the model, or to use a change detection approach where the incidence angle is consistent over time. But I myself wouldn't necessarily advocate for applying an incidence angle correction, because I think you could possibly be introducing error into your soil moisture retrieval. Question 18, are crop classification maps available through Agriculture and Agri-Food Canada? Yes, that's an easy question. So all of the crop classification maps that we produce, we do them every year, and we have been doing them since 2008. All of those maps are available through the open government portal of the Government of Canada, so they are all freely downloadable. They're usually not available until well past the end of the season. But once they are produced, then they are downloadable. And if you need access to the website, just let us know and we can send you the web link. Question 19, how do you calculate the biomass and how many images would you require before, during, and after the season? How would you detect disease if it's new? So for the biomass retrieval, we have an international project that we're leading called GeoJCam. And one of the things that we're doing is we're testing different biomass retrieval methods. Most of them are semi-empirical models, so we are focusing mostly on the water cloud model. And when we did a sort of consensus of the international community, most of us are using the water cloud model. One country that we're working with is using a purely empirical model. So we're using a water cloud model, which requires collecting some ground data to parameterize that model. So we need information on soil moisture and biomass. And then we create a parameterization of the water cloud model. And then what we're doing is similar to the IEM model, we're building lookup tables. And so once we know what the expected backscatter is dependent on different biomass and different soil moisture, then we use a lookup table along with a new radar acquisition to provide an inversion of the water cloud model. In our particular version of the water cloud model, we're using 2 polarizations to do the retrieval. So typically VV and VH polarization. If you do it that way, then there's no requirement to put any ancillary information about soil moisture into the model. So because we have biomass and soil moisture as 2 parameters in the model, we can, with the lookup tables and 2 polarizations, we can invert the model for biomass or soil moisture. Others are using the water cloud model, but they're using ancillary soil moisture information into the water cloud model to estimate biomass. So there are some disadvantages of that because you would need to have soil moisture information to do that retrieval. In terms of how many images you would require before, during, and after, for this water cloud model, once the model is parameterized, then you can retrieve soil moisture on an image-by-image basis. So again, if anybody wants access to publications on how we're doing this and what the results have been, you can contact me. Or if you're interested in being part of this international project where we're testing the biomass retrieval, then you can contact me as well. And the last part of that question is, how would you detect disease? So that's a really tough one. And again, thinking back to if we're looking at trying to detect disease directly, if we think back to the principles that we learned in the webinar, you really have to see a change in the crop structure in order to see an impact on the radar backscatter. And usually by the time the disease affects a structure in a crop, it's really too late for intervention. Having said that, we do have a project at Agriculture Canada now where we are trying to develop a disease risk tool. And here we're sort of building a decision tool that is looking at soil moisture from radar data, as well as cropping history, and a few other variables into a disease risk assessment tool. But here we're bringing together information on soil moisture conditions, as I said, cropping history, and rainfall and temperature and that type of thing. So the best way, I guess, what I'm saying on the disease part is to integrate data from all of these different sources. And again, if you're interested in this disease risk tool that we're building, you can contact me and I can give you some more information on that. Question 20, with regards to the classification training vectors, how were they prepared? They didn't seem to appear on the map. Okay, I think let Nina answer it, but I think they were there, we just couldn't find them. It was the color or something, but I'm going to let Nina answer that.
Yeah, so for prepare the training data, so we do supervised classification, we need training data. So I prepare the training polygons, use ArcGIS. You can use QGIS. You just prepare the shape file for each crop you want to identify. For this example, I have 4 crops need to identify. So I have 4 shape file, and import that shape file to snap file. So when I do the demo, so it's difficult for me. I forgot some location, but I only have 5 polygons for each crop. so it's hard for me to find the polygons, but the polygons do displayed on the map. I apologize for this. And the next question is the number of look, range, and azimuth are assigned 3 by 3. Is that any specific number related to any particular tree, or is if I use 5 by 5 will do better? And think for future process, when you select the filter, you need to specify which window size you want to use. This window size truly depends on the target, which target you focus on, you interested in. For 3 by 3 and 5 by 5, for all experience, we try different windows and visually examine which window size is better.
Okay, question number 2. How to identify sown area on Sentinel-1 image? This is a kind of a general question. You know, again, I think the best process is probably through a classification process, and Nina showed you one classification process, but there are many other different classification methods to use, but sort of again a multi-temporal acquisition using VVVH imagery is probably the best way to go. I wanted to say as well, in Agriculture Canada, and we have a very similar method to what the U.S. Department of Agriculture uses. We use for our classification purposes, we use a decision tree methodology. So when we were developing our crop inventory method, we tested a few different methods. And we determined that the decision tree, which is a supervised classification, provides the not only the highest accuracy, but the most consistent and repeatable accuracies over time. So again, our methodology is very consistent with what the U.S. Department of Agriculture uses. The next question, I think, is as well a processing question, so I'll hand that back over to Nina.
Yeah, so for this demo, I just step by step show how to process the radar cell 2 data and the Sentinel-1 data. If you use a snap, there is a graph tool. So you can use this graph to process the image for several steps. So that's one graph tool. If you have many images, several images you want to process, with a snap, they have a batch processing tool. So if you're familiar with the snap and know the processing steps, you can use the graph tool and the batch process to process the image faster and efficiently.
Okay, question number 4. Can radar distinguish between surface water and the fully saturated soil? That's an interesting question. And we do have in Western Canada, we have a situation where we have soils in our test site that can become very, very saturated. So where the volumetric soil moisture is close to 60%, which is very, very, the pores are very, very full. So the answer to this is yes, because the scattering mechanisms are quite different. So when we have, you know, even a thin film of water on the soil, what drives the scattering at that point is that surface scattering. So if you have even a thin layer of water on top of the soil, what will happen is we'll get this forward deflection or surface scattering right off of the water itself. Whereas if we have if there's any penetration into the soil, because we don't have that film of water on top of the soil surface, then we get some penetration into the soil, and now it's the dielectric in that case that's driving the process. So they're really different scattering processes. So one is a surface scattering, specular scattering, that's the word I was trying to think of, specular scattering, and mechanism, and the other one is driven by the response from the dielectric constant in the soil. So I think this is the last question. Apart from performing a classification on the image, what are the other techniques that can be applied on SAR imagery for agriculture study? Is there any indices techniques available? So this is another great question. Absolutely, we just showed a couple of examples here, but I think I've already alluded to the fact that we have some methodologies that we've developed where we're retrieving biophysical parameters from radar data. So we talked about biomass a little bit, above ground biomass. We also have a similar method using the water cloud model to retrieve leaf area index, which is a very good indicator of crop productivity. We worked collaboratively with a Canadian company in Canada where we were able to through a methodology that they developed, which is a sort of an artificial intelligence methodology where we were able to estimate the phenology of canola crops, so what growth stage the canola, and that was entirely driven by the response at X band with TerraSAR X and C band with RadarSat 2, so that's crop phenology. And actually Nina and I are working right now on a methodology to derive sort of a radar index. There are some indices that have been published already. The RadarSat Vegetation Index is one, but we're also looking at other radar indices besides the RVI, the Radar Vegetation Index, so other radar indices that would be highly correlated with NDVI so that we can integrate radar-derived vegetation condition with what we see from NDVI products. So there are a number of other applications. There's also been some research looking at whether we can derive information on tillage, and that has been a tougher go of it. We do have some publications on that as well. And we do know that radar is driven by surface roughness, as we heard. But the struggle there is that the different tillage implements can create quite a range in roughnesses. And so it's really difficult to, for example, identify a tillage system like a moldboard plow or a chisel plow from the radar imagery because the variance in the roughness that those implements produce is quite significant. But if we are looking at things, for example, identifying whether a field has been tilled or not tilled, so whether it's very smooth because it hasn't been tilled or it has some roughness because it has been tilled, then there has been some research done on that, mostly looking at change detection approaches. So lots of other things as well that have happened. So I think, Erica, that's the end of the questions.
Yes, so thank you very much, Drs. McNairn and Zhao. And thank you to all of the participants today for tuning in and for your enthusiasm with all the questions. And just to remind you that we have one more webinar in this series, and that will be on Thursday, same time, and that will cover interferometric SAR for earthquake monitoring, so looking at surface deformation. Wishing you all a good day, and until the next one. Bye-bye.